All right, let's get started with our final lesson. I will actually do a redo of lesson 1 because I didn't capture it on camera, unfortunately. And at some point, I want just to give people this to have it as like a blog seminar, and I don't have to hold it over and over. It is nicer if you're there and you can actually do feedback, but I also cannot always do this course, so I'll try to redo it. If anyone of you guys want to visit me with that, we can talk. I don't have a specific time on it, but I want to do it next week. I know for Rio it might be nice because he missed lesson 1. If I redo it anyways, that's good. And then we can have a little bit of a conversation, because it's also good that I see how good you understand something, and feedback is always good to have an actual good lesson. Okay, anyways, so today there's quite a lot of topics that we want to capture that we learned in continuous domain and that we also want to do in discrete domain, and they should work, but they might be a little different. So let's see. But first we might want to start with homework. We can talk about it because I think it's quite a challenge to do it for the first time, right?
A lot of mysteries there.
A lot of mysteries. Mistakes? Yeah. I'll be right back. I get some better chalk from here. Yeah, we might turn it off and on. Okay, so first of all, for the homework, we try to do the Z-domain model of our class, right? So that hopefully wasn't really that big of an issue, because it's really close to our example 2, right? The differential equations look the same. The B is basically the R, and L over R is the tau, so it should look the same. So what did you get as NSD of Z?
In this thing, I have in routing Cook method. There is 1 minus Z power minus 1.
So maybe you just give us the, okay, let's start with the cookbook method. What did you get as NSD of Z?
So that's one, you mean formula?
Yeah, what's your transfer function?
Okay.
Or maybe I just write it down. So in both cases you should wind up with the same thing.
Yeah.
If you don't, go back to lesson 3 and look how we did it together on the board. Because that's literally the same pair of differential equations, but it's the same differential equation, just B is the same as R, and L is the same as M. And we'll see it's the same math, because those systems actually from differential equations look very, very similar. So you should wind up with both ways of doing your math at an equation that looks like this. Right? Okay. So usually from that point on, when I do my math, I try to simplify it to just see what it is. So this has a gain, and very commonly when people write this kind of polynomial, or this break, they would do it in this format. Right? That's basically what it is. Those are just variables. Those are just constants basically for our system. Okay. And now we want to basically compare it to our to the approximation box, right? So then we have the one that I gave was the forward rectangular version, and that basically looked at it. One down. That's this one, right? Down here. Since it's on my camera, I'll just redraw it very quick. So we basically approximate our integration with this here, right? And then we still have the u1 over L, and with feedback over the R. Right? And with Mason rule, we should come up with the transfer function, and let's call this direct discrete, and this will be our NSD of using the approximation of the rectangular. Let's call this rec. And we will wind up with something that looks like this. Okay? So it also has its so it kind of looks similar, but the values obviously are different, right? So these two would be the same if T over L was almost the same as 1 minus e to the minus T over 12 over R, right? And at least for the gain. And for the pole, it's true when 1 minus T over 12 is roughly e to the minus T over 12. Right? Yeah. That is approximation, is actually a pretty good approximation. And we can already see, if we look at the pole, that's really important for our dynamic attributes, right? We can already see this goes basically like it's like a straight line, right? It starts at 1, and the rectangular just goes down like this. If I have T over 12 on the x-axis, and the y-axis I have my pole. So, and exactly when T and tau is 1, when they're the same, that's when it reaches the 0. And this actually looks like this. Right? At infinite it reaches 0, but it will definitely never get negative. So when you're around here, it might be a good approximation. Once you get close to this direction, it really gets worse and worse and worse. And then we have the Tustin. Really looks very different because there, in this block, we have this, so the Tustin looks like, let me see. Looks like this, T over 2, 1 plus e to the minus 1, 1 minus e to the minus 1. Right, and then the same R back group of 1 over L cubed. And then we do Mason's rule, and can also get the closed transfer function. And it will look like it has a gain. Looks like this. Okay, so the format looks really different. It also has a gain. But up here, it actually totally different, right? So there's a 0 actually. This one does not have 0. And the B also looks different. But especially this up here, right? Looks very, very different. So the pole 0 plot actually So if you look at this pole, and also draw it here, so that's, let's say this here is the direct discrete. This one's the rectangular, and the Tuscan will sort of look like this. And it reaches 0 at t over tau 2. Okay? It is, from the pole perspective, actually closer to the direct discrete, or the actual pole, even at really bad t's, but it becomes very, very wrong also at some point. And even this good area, where the rectangular seems to be a really good approximation, it still has this wrong 0. And we'll see what this does. It's like, it's really, really different in behavior. And the rectangular one can be a good approximation for this system. It depends totally on how the differential equation looks like. With different differential equations, and you get the actual ST of z, this will always look different. Except when the differential equation is literally the same. But if the differential equation is a little bit different, these approximation models will be totally off. Or they can be, or maybe a different one becomes a better one. But it depends on the physical system which one can be a good approximation, and also just within a certain area. But this is always true, and you should have seen this in your own one. You can play with t whatever you want, it will always be a very good approximation. Oh, no, not an approximation, it's always exact, this exactly the same as your continuous.
How do you find which speed and all?
Which is what?
Which sample length and all sample?
That's the one that your system basically tells you, right? It could be your switching frequency of your switches, right? So if you design an inverter, you have a switching frequency. Technically, you can do twice as many sampling as you're switching. That's with the PWM, that's a different topic that we can talk about. But it's basically related to your switching frequency, for instance. In other systems, it depends. You can choose the sampling time. And you actually see in your zero pole plot in Z domain that your poles move off the plant depending on your T, right? So it might be also a good idea to think about your system and what sampling time makes sense. Because sometimes you actually sample way too fast and all the poles go all to the one, right? And they all basically look the same and it's hard to separate them. Maybe it's a good idea to actually not sample as quickly. And there are some examples where it's better to not sample as quickly. So really fast sampling is not always the solution, that's what I'm saying. It's just the solution to get bad approximation work correctly. Then yes, sampling helps. As you can see, t goes to 0 and all of these approximations seem to be pretty good. Okay, so and we'll have a look at this, I'll show some of these plots on the laptop, but first I want to talk about root locus again. So we talked about root locus in continuous domain a lot, a little bit in Z domain, but there should have been something weird happening when you look at command tracking in the homework. Did you see something funny happening with the face of your command tracking? Gyonandra, did you have a look at your command tracking? What did the face wind up?
Face.
The face of the control. So in continuous domain, what's the final value of your phase? If you have a PT1, for instance, or you don't have a normal control, what did we say? We start at 0, right?
Yeah.
The command tracking goes to where?
90.
Minus 90, right? And you should have seen something else happening in discrete domain. But maybe you didn't see it.
I plotted magnitudes.
You got what?
I plotted magnitude, not angles.
Okay. Always look also at your angles because the angle information is really important as well. Anyways, let's reiterate very quick on what happens here. So let's get back to the root locus in Z domain. And again, so we had this formula already, but now we do it on Z. So the magnitude should be multiplication of all the zeros. This would be the poles. Right, so that would be basically the amplitude And with the angle we have the same as also the same equation. It will be basically the angle of the zeros minus the angle of the poles. And if we now look at this in the Lucas, so what is Z?
E power omega j omega t.
Is e to the j omega t, right? So where is this in the Z domain? If I now increase the frequency, where do I start at zero? At zero. I want to evaluate this at different frequencies, right? So let's start with omega at zero. It starts here, right? At 1. And what with increasing frequency, what do? We do a circle, right?
Yes.
It's a rotating angle. So we evaluate on this unity circle. Right? So what is the value up here?
1. Okay.
So this is omega times t, right? And up here, the angle is p over 2, right? So omega t equals, up here, omega t equals pi over 2. So omega equals pi over 2t, right? And here, omega equals pi over t. And we could keep going, but what is this frequency? Have you ever seen this?
That's
It's Nyquist. Have you ever heard of Nyquist? The Nyquist frequency? Nyquist frequency tells us that Fs, or the sampling time over 2, is the maximum frequency that the Z domain really makes sense. Because after that, you cannot really modulate a sine wave anymore. If you have 2 points, you can basically have both magnitudes, and maybe you can extract the frequency and the amplitude from that. But really, if you do it less often, it doesn't make any sense anymore. Right? So that's the absolute maximum that any of this makes real sense. So we have to be lower than that. So in our case, that means that's 1 over 2t, right? And if I put that in cases of omega, so what is now omega max? Is this times 2 pi, right?
yeah.
So what's that? That's pi over 2, right? Or that's the Nyquist frequency. So really, we can only go from here to here, and then everything down here doesn't make sense for the frequency evaluation. Okay? So now think about any pole. Let's try different examples of poles here. Let's start with poles. We have a pole here, okay? We set our pole, this green one, somewhere on the right side. It doesn't really matter if it's on the right or not. But so what angle would we start with here? So it will be, where does it start? So I start here, right? So what's that angle at frequency 0? It's 0, right? So it starts with the angle 0. It goes up, 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 up. At some point, we have 90 degrees, right? So it goes to 90, but what's at our Nyquist? Yes, minus 980, right? So it actually goes to 190. That we don't see in continuous domain. Yeah. Okay? So we have a break frequency at 45, but you will see that it sort of breaks again. But it's all the poles that are in the middle do this. And you cannot choose what that frequency is because that's just Nyquist happening. If you have a break frequency way left of the frequency domain way left of the Nyquist frequency, you will see 2 breaks. If you get closer, you basically see one big break from 0 to 180. It depends where you put this pole. But this one you cannot choose. This will always happen. It goes down to 180. Okay, so that would be this case. Then we could also have a pole here, right? What is this pole? That's an integrator, right? This is the slowest pole possible, so that's an integrator. So what angle is this start with? Imagine the smallest frequency up here.
Then it's like.
It's basically starts, yeah. So in the logarithmic plot you never have 0, and at 0 is not really defined, but once it's like even tiny big, you already have 90 degrees, right? Where it's actually minus 90, because it's a pole, not a 0. And it goes also to minus 180, right? So an integrator will have this funny behavior, because it doesn't really break, but it will have the Nyquist. I mean, it will sort of look like a break. So an integrator doesn't break, but in discrete, it sort of does. And then you have this brown one. Where does that start? It starts at 0, right? And goes to where?
Minus 90.
Minus 90. Correct. And that's, I'm just doing this because I want you to understand what's going on when you look at your Bode plot. Because the first time you should have looked at your geometric and you get this behavior, you should have been baffled because I don't only have one pole, why does it go to minus 180, right? And that's because of this. It's the Nyquist that does this. Okay?
Plus 90.
So this here starts at 90, right? And goes to minus 90. Starts at 0 and goes to minus 90. There's very little bit plus 90. And there's one very special pole in here as well. Which one would you also consider something very interesting? There's one point that we have to look at that has a very unique property. So all of these, so we have one that has basically delta 90, we have one that has 180, 90, 90. And we have one that has a really interesting property. So what's the phase here for this the origin? It also starts at 0 and goes to minus 180. That's basically true for all of the poles within the unity circle. But these have really interesting properties for their magnitude. Now let's look at the magnitude. This was all for the phase. Now let's look at magnitude. The green one, basically, the magnitude just goes down, right? So at early angles, the magnitude doesn't really change, and at some point it really fastly goes down, right? And at this point, let's look at magnitude. And we plot this back here. So we can plot it here. So the green one starts at whatever this is, right? And it doesn't really change a lot in the beginning. And then it starts to go down really quickly around these angles. But what does it do after? So for instance, if we draw the Nyquist frequency, what happens at the Nyquist frequency? So imagine this doesn't change a lot here. The magnitude, right? So the magnitude is the length basically of this and 1 over, right? So in the beginning, we start here, and the magnitude doesn't really change all that much. At this point, it starts to change a lot. But what about here? Is this significantly different to this? No. In continuous domain, you see like how it just like goes down and on and on and on, and almost to 0, right? This doesn't happen here. Interesting. It actually, imagine it would keep going. the magnitude would actually go up again, right? So interesting, you should see something like this that stagnates at Nyquist. You can't go further really, because after it doesn't make any sense, but that's how it looks like in the Bode plot. And it's really because of this. That's why I try to draw this, and if you look at your Bode plot, oh, that's why. Because it looks really funny. Okay, and then let's have a look at the integrator. Yeah. This one?
Yeah.
Okay, so if you look at these, right, these two basically have the same length, right? So 1 over that, it shouldn't really change.
Yeah.
Up here, let's see, this and this already have a big difference, right? So 1 over something bigger, it really starts to break.
Yeah.
But in the end, so usually, like in continuous domain, this doesn't happen. It doesn't wrap back, right? You just keep going on the imaginary axis up and up and up, and then obviously it's infinite and infinite. But here, there's no such thing. The circle will close again. So at some point, it will actually not grow bigger, right? So these two are basically the same length. So I know around Nyquist, it actually stagnates. The magnitude doesn't change anymore. And it actually is, the gradient of it should be pretty much 0 at this point. Because after that, it would actually come up again. So just mathematically, you know it should sort of look like this. Okay, let's do the integrator. What would the magnitude be at infinitely 0? Or at 0, sorry. 1 over 0, so infinite, right? What we would expect of an integrator, right? It starts at infinite gain, and what would it look like at Nyquist? It should also stagnate, right? So we will sort of see, so this is logarithmic, it goes down like this, but it will at some point just do this. And what about this on the left? So the stars are really changing a lot, right? And what in the end? It drastically changes, right? It goes to 0. Right? Makes sense? Yeah. So it actually does this. Makes sense? It doesn't really change in the beginning, the length doesn't really change, but around here it drastically changes and it goes to 0. Or wait, infinity, sorry. Yeah, you're right. Yeah, infinity, sorry. So it actually, it starts at something, something's there and it goes like this. No, you're right. And, yeah. Wait, did we do it here correctly? Yeah, it stagnates. Oh, that's great. And then we have this guy here. What is the magnitude doing on this guy?
It remains constant.
It remains constant. Yeah. Exactly. It remains constant. But the phase changes. Right? It's just, literally it's just the circumference. It's just, you're absolutely right. The magnitude will never change.
The phase will be similar to the first phase.
Yeah.
But the magnitude,
the magnitude is constant. So that's like something that's impossible really in continuous domain, because it basically means that, or it's sort of what we do with command tracking really, but it's an infinitely fast pole. Here's the bandwidth is basically infinite. And if you look at a system that looks like this, you will see that it basically can just step. You put something in there and it steps to a point and it never changes. It already got an end value and it's there. And we also call this behavior where it steps to whatever it doesn't have like a PT1. So basically what we're doing is we're getting faster, 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 and at infinite, it only looks like a step. And this we call a deadbeat. Or deadbeat behavior. This is weird, I don't know if you know this term from English, it really has a really bad connotation. Deadbeat is like a loser in life. I don't know if you have heard this word. But actually we use it in controls for this because the whole thing is dead in one beat. Within one sampling period, it's settled and it reaches final value. That's why we call it deadbeat. Also, deadbeat control does this. It will have this behavior. And what it is actually it's a pole at the origin. Okay? It's a deadbeat behavior. But yeah, don't take this like the word what deadbeat means otherwise.
Yes, actually I had that opinion. That means something creative.
Yeah, so it has a really bad connotation, not so much in controls. Okay. So that's just for the root locus, and now let's look at the homework. I should probably turn up the lights for this. So I hope you can see this all right. Okay, so first I want to have a look at this. That's what I basically told you. What I'm plotting here is the task in the direct discrete and the forward and where the poles are situated, depending on t over tau. So in the homework I basically said we should change t and look like how good are these approximations, right? And there are some, and as you see, like that they're pretty much the same. The Tustin is okay, but but it still has the zero. So you will always see in a time plot they look really different. But the pole approximation is pretty okay. And our example for the nominal, I said like 0.005 is something, right? So that's somewhere here. All of them are pretty much the same. And here I plotted the percentage error in the position of the pole over t over tau. So actually if we're down here, it's around 1 mil, so 0.1% within the accuracy. So that's fine, that's better than our measurement anyways. So at that area we're good with the approximation, especially with the forward rectangular version, because the poles in the zero are actually really, really close to what they actually are. However, we do direct discrete modeling, so we don't really need this, but if we ever feel like it's hard to derive it, we sort of know in what area we should be. But this depends on the system, right? In some systems, this plot might be totally different. But just for this case, we see how good the approximation is. Okay.
Is it only for the pole?
This is just for the pole. Not like the gains are also very close around this, but they're never perfectly accurate. But the direct discrete is, and you will see this when you do any of these, and we'll do this. We'll try, especially these two attributes, because this is really interesting. If you look at when t equals tau, where's the pole now of our forward rectangle? The pole is now at the origin, right? So we should see a deadbeat-like solution, right? So if we test our system at t over tau is 1, we will see something funny happening. And also at 2, the Tustin is also a deadbeat. Okay, and you will see this. Okay.
Is there any comparison in zero?
What do you mean in zero?
In zero, how about the methods like Tustin and rectangular or even direct? Is it like transfer directly zero from continuous element to?
So you're saying if you do zero TS, is it the same as continue? What's the question?
The zero in S term, is it the same when you do the approximation or you do the direct transfer?
Oh, where the zero moves? Yeah. So of the rectangular one, since we don't have a zero, yes. But the Tuscan has a 0, so it's always different to the actual one.
Yeah.
So yeah,
Our direct template, is it the same? Or?
the direct discrete is the real one. So it's exactly the same as the real one. Yeah. So that's the actual solution. So it is what it is. And you can test it. You can test any T. You can test any dynamic plot. You will always see. And I'll do this. So this is sort of what I expected you to build if you had time. For the modeling, here is and I'll zoom a little bit in. That's what I always assume to be my real model. I put a voltage in, I do a zero order hold, right? So it's my latch, and I have an actual continuous system, and then I sample it. And I only look now at the current of the actual one. So down here is the Tuscan approximation, as I've drawn it, right? Then I use the forward rectangular one, and down here is our direct discrete. And you will see you can put any parameters, you can put any T over tau, they will always match. And let's try this real quick.
Do you need to add some zero there when in the grid DOM if you have like 9 or